Today, I'm going to talk about light. Light is an electromagnetic phenomenon. And already in the 16th century, way before Maxwell, a lot of studies were done of the interaction of light with water and with glass. And the kind of experiments that were done as follows. Say this is air. I call that medium 1. And this is water. Call that medium 2. And I have a light beam that strikes this surface. Light comes in like so. And I define this angle as the angle of incidence. And I call that theta 1. This is the normal to the surface. We call that the angle of incidence. I will see now that some of that light is reflected with an L as in lion, and some of that light goes into the water, and we call that refracted with an R as in Richard, and this angle we'll call theta 2. And it was a Dutchman, Willebord Snellius, who in the 17th century found 3 rules that govern the relation between these 3 light beams. The first one is that this beam, and this beam are in one plane. As you see, that is my plane of the blackboard. The second thing that he found, that this angle, theta 3, which is called the angle of reflection, is the same as the angle of incidence. That was known before him, of course. And then the third one, which is the most surprising one, which is called after him, which is called Snell's Law, although his name was Snellius, is that the sine of theta 1 divided by the sine of theta 2, if we go from air to water, then that ratio is about 1.3. If you go from air to glass, it's a little higher. It's like 1.5 or so. He introduced the idea of index of refraction, which I will call N, as in Nancy, index of refraction. For vacuum, the index of refraction per definition is 1, but it's very closely the same in air. We always treat it as 1 in air. And in water, the index of refraction is approximately 1.3, and in glass, depending upon what kind of glass you have, it's about 1.5. And so we can now amend this law, Snell's law, by writing here N2 divided by N1, N1 being the index of refraction of the medium where you are, your incident beam, that's why I put a 1 here, and 2 being the index of refraction of the medium where you're traveling to. You refracted into this medium. And so you see indeed that since water is 1.3 and air is 1, that this ratio for air to water is 1.3. And this is called Snell's law. And it is immediately obvious that if you go from air to water, or you go from air to glass, that angle theta 2 is always smaller than the angle theta 1, because this number is larger than 1. But if you go from water to air, then the situation is reversed. And that's what I want to address now. That's actually quite interesting. So now, my medium 1 is now water, and my medium 2 is now air. And so now, I go from here to here, and so here I have my angle of incidence, theta 1, and here I have my angle of reflection, that is this theta 3, and now here I have my angle theta 2. And so if I write down now Snell's law, then I get the sine of theta 1 divided by the sine of theta 2 is now n2 divided by n1, but n2 is 1 divided by 1.3 if we go from water to air. And what is so special here is that theta 2 can obviously never be larger than 90 degrees. And so if you substitute in here theta 2 is 90 degrees, then you will find that theta 1 then is about 50 degrees. And if you apply this equation and you substitute for theta 1 an angle larger than 50 degrees, you're going to find the sine of theta 2 being larger than 1, which is nonsense. It cannot happen. And so nature ignores Snell's law, and nature says, sorry, I can't do it. And what nature now does, if the angle of theta 1 is too large, in this case with water larger than 50 degrees, this is not there anymore, and all the light is now being reflected off that surface. And we call that total reflection. Total reflection. So total reflection happens when theta 1 is larger than a certain critical angle, and the sine of that critical angle, for which I write CR, is n2 divided by n1, but there is a condition, and the condition is that n1 must be larger than n2. If that's not the case, then there is not total reflection. And total reflection is actually very interesting. It has practical applications, which I will discuss with you shortly. But I first want to do a demonstration in which I want to show this to you. I have here water, and here is air. And I have a laser beam which I can shine in, and I can change this angle theta 1 and slowly increase it. And you will see that when I approach the 50 degrees, first of all, you will see that theta 2 increases, and then when I approach the critical angle and exceed it, then we have 100% reflection. So let me first turn on the laser so that there's a little bit of light, and I'm going to show it to you there for those of you who are not sitting very close. And that means I have to set the light situation. Okay, so there you see the light coming in just the way we had it on the blackboard. This is the way it comes in water. This is the reflected part, and this is the one that is refracted into the air. So that is this one here. And now I'm going to increase that angle. When I touch the table, the water will start to wiggle a little, and you will probably see that. So I'm going to, I'm going to increase that angle. Look how I'm increasing it. Look, that theta 2 is getting larger, is going to approach the 90 degrees. I increase theta 1. I increase theta 1. Look at theta 2. Almost 90 degrees. I'm very close to the critical angle now. I'm almost at it right now. And now all the light is being reflected. 100% reflection. A remarkable phenomenon. And this has practical applications. And we're going to show you some of these practical applications too. The most important practical application is fiber optics. If I have a fiber and it is properly designed, so this is a fiber, and some light comes in here, and it hits here, so this is, say, some plastic or glass, and this is air. If this angle of incidence is larger than the critical angle, 100% reflected. And so nothing comes out in the air, 100% reflected. Here, again, the critical angle is exceeded, and so 100% is reflected, and you can go through this whole thing for miles on end. You can put even knots in there. As long as you never exceed the critical angle, that light will propagate, and there will never be any loss of light. And that's why people are very much interested in it. You can transport even images, as I will show you, through fiber optics. I have here a fiber optics which has 4,000 fibers in it, 50 microns in diameter each. And we have a laser beam here. And the laser light will come out. I will show you the laser light shortly there. And it doesn't matter what I do with the fibers. I can even go 180 degrees and shine them there. As long as inside the fiber, I always exceed the critical angle. I don't want the television anymore, so we can turn this off. And let's here have the laser light. There it is. Here you see the laser light. Okay, now look at this bundle that I have here. I'm turning it into an absurd snake, almost like an S. All the light still comes out. So it goes all the way through. I'm going to turn it 180 degrees around, turn it to the wall there. There it is. So there's an amazing phenomenon that this light doesn't get out in the air, it stays inside the fiber, and that's the idea behind fiber optics. I have another application of fiber optics right here, which is very similar. You can send an image through fiber optics. This is my fiber optics now, thousands of small fibers. And I send a message in here. This side, an image, could be a person, could be a text. And here we have a TV camera. And we can watch that image. On this side of the fiber appears that image. And this television camera will be able to see that image. And let's see whether we can show you that message. Okay, have to do something here again. I think you're going to, there it is. So you actually can see the individual fibers. You see them? How interesting? Each one, these are individual fibers. And their diameter is probably not much more than 50 or 100 microns. Let's see what message there is for you. Oh man, exam 3. You don't want to hear about that, do you? Well, it depends on what the message says. Problem? No. No. Problem 1. Problem 1. The figure, below. Oh, I must have, that's the wrong message. I couldn't possibly meant to give you away the exam, of course. So I apologize for that I showed you the wrong message. But at least it demonstrated to you that you can send an image through fiber optics, even secret messages.